Now, let's consider the operation of two water distribution systems. In both systems, the utility tanks have 40 meter cubics of water. However, consumer A only needs 30 meter cubic, while consumer B requires 10 meter cubic of water. Based on the consumer's demand, this system will perform a step-down function. Firstly, switch A and B are turned on to allow the water-generated tanks to generate and store water according to the consumer's demand. At this moment, we can see there is a continuous water flow between the utility, water generated, and consumer tanks. Thus, as similar to this condition, when the transistor in the DC converter is turned on, there is a continuous current flow between the DC supply, inductor, and resistor. In this condition, the inductor is energizing to store the magnetic field. Once the water-generated tanks completed their tasks, both switches are turned off. Automatically, the uncontrollable switches are turned on. At this moment, the utility water tanks are disconnected from the consumer's tanks. Hence, the water-generated tanks will act as the water supply to the consumer tanks. Thus, in the operation of the DC converter, the turn-off transistor will disconnect the DC supply from the load, and eventually the inductor will de-energize to supply current to the load. Based on your observation, which switch should be on longer to generate water in the second water tank, where this water reflects the consumer's demand? The answer is A. Due to the demand, the turn-on time of switch A is longer than switch B. Hence, it will affect the duty cycle of the switch since the turn-on time is directly proportional to the duty cycle of the power switch. Based on these two systems, switch A has a higher duty cycle than switch B. Lastly, let us compare the system diagram with the circuit topology of the DC-DC buck converter. According to the equation, if Vs is constant, hence the output voltage is directly proportional to the duty cycle. Therefore, it verifies the conclusion made in this discussion. Next, we will consider a new topology of water distribution systems. Take note to the new location of both controllable and uncontrollable power switches. As similar to the previous systems, the utility tanks can generate up to 40 meter cubics of water only. Nonetheless, consumer A and B requires a higher volume of water, which are 100 and 70 meter cubics respectively. Thus, this system must perform the step-up function to meet the consumer's demand. When switch A and B are turned on, we can see the water-generated tanks are generating the additional volume of water to accommodate the consumer's demand. At this moment, water will flow between the utility tank to the water generated tank only. Thus, we can say that these systems are executing the boosting function. Therefore, in the DC converter circuit, the inductor is called the boost inductor. To perform the boost function, the inductor must solely be connected to the DC supply. Hence, the load must be disconnected from the source. Once the water generated tanks completed their function, switch A and B are turned off and automatically the uncontrollable switches are turned on to connect the consumer tanks to the systems. At this moment, there is a direct water flow between the utility, water generated, and consumer tanks. Thus, in the DC converter circuit, the connection between the DC supply, boost inductor, and resistor is established when the transistor is turned off.